All right, we're going to talk now about exact and inexact numbers, uncertainty, and introduce significant figures. And this corresponds to sections 2.3 through 2.4 of your textbook. So first off, when performing scientific calculations, numbers can be grouped into two general categories, what we call exact numbers or inexact numbers. So an exact number is a number whose value has no uncertainty associated with it, and we know the value exactly. So exact numbers are usually things that are definitions or objects that can be counted. So examples include there's 12 donuts in a dozen, there's 100 centimeters per meter, or there's 3 atoms in 1 molecule. So these are things that can be counted, like 12 donuts in a dozen or 3 atoms per molecule, or they're by definition, like the metric system prefix table says by definition there's 100 centimeters in 1 meter. Inexact numbers is a number whose value has a degree of uncertainty. So these usually arise from measurements. And so anytime you're doing a conversion between one system of measurement and another, it almost always includes some sort of inexact measured numbers. So when you're taking a measurement, the result is going to be an inexact number, because when you take a measurement, there's always a little bit of estimating that happens. And when you're converting from one system of measurement to another, at some point a measurement was taken to do that conversion to figure out how many grams are in 1 pound. We had to measure that. And so to convert from grams to pounds, that also includes an inexact number. So examples, if you measure a length of paper is 11.5 inches, that's an inexact number. The density of water is 1 gram per milliliter. That's an inexact number because that number was obtained by taking a measurement in the lab. There are 2.2 pounds per kilogram. Converting between pounds and kilograms, that's an inexact number, because to come up with that conversion factor, it's like a scientist in a lab somewhere had to take 1 kilogram and place it on an English scale to measure how many pounds it was equivalent to. And so to come up with a conversion factor involved taking a measurement. So the prefix multipliers in the metric system are all exact numbers because they're all definitions. And so when you're dealing with prefix multipliers, you're automatically dealing with exact numbers. So let's do a quick concept check. Which of the following statements contains an exact number? The thickness of a sheet of paper is 0.0045 inches. The size of a sheet of paper is 8.5 by 11 inches. The number of sheets of paper in a ream is 500, or no correct response. You should come up with the answer C. The number of sheets of paper in a ream is 500. That's an exact number, and that's the example of a counted exact number. You can count out exactly 500 sheets of paper, and by definition, 1 ream of paper is 500 sheets. The other options all involve measurements. So inexact numbers are going to arise from the uncertainty that's inherent in measurements. So every measurement carries some degree of uncertainty. So if you think about measurements, right, a measurement is comparing an object to a standard. So in the image shown, our object is the green bar, and our standard is the ruler that's in centimeters. So when we're measuring our object, the green bar, we know with certainty the values marked at each line or graduation on our measuring device. So our ruler has markings every 1 centimeter. But to get our measurement, we actually estimate between the markings to get a more accurate measurement. So when we're reading the length of the green bar, we might estimate that to be 3.7 centimeters. We know it definitely lies between 3 and 4 centimeters. And then we estimate how far between those two markings it actually lies. And so that last digit, the one that we estimated, the 0.7, that's what produces the uncertainty in the measurements. And all measurements have this uncertainty, whether it's an analog measurement like shown here, where it's a person reading an analog measuring device to come up with that uncertain digit, or whether it's a digital device where the digital device is actually doing the estimating part for you. So what digits are certain in each measurement and what digits are estimated? So the certain digits are the ones that are marked on the measuring device, and the uncertain digit is the one that's estimated between the markings to get a more accurate measurement. So if we compare these two rulers, ruler A and ruler B, ruler A has markings every 1 centimeter. So when you estimate between the markings, you can kind of in your head divide up ruler A between the markings into tenths. And we'll see if I can do this somewhat accurately. Something like that. And then after you kind of divide it in your head into tenths, then you come up with this estimate that the green bar is 3.7 centimeters long. So with no certainty, based on the markings on our device, that it's between 3 and 4, and we estimated that it's 3.7. If you have a better measuring device with markings closer together, then because your markings are closer together, you get an even better, more accurate estimate of that measurement. So in this next ruler, we have markings every 1/10 of a centimeter. So these ones that I came up with, this is a better, higher quality ruler. It has more precise markings. So now when we're estimating between the lines, we're actually estimating between the 3.7 line and the 3.8 line. We know with certainty that it's definitely between 3.7 and 3.8 because we can see that with the markings on the ruler. And then we still estimate between these lines one more digit. So that's how we get 3.74 as the estimated reading for the green bar when measured with this other measuring device. So the digits that are certain in both of these measuring devices, the digits that's certain in measuring device A, ruler A, we came up with our measurement 3.7. The 3 is certain, and the 0.7 was our estimated or uncertain digit. In the second ruler, our measurement was 3.74. Both the 3 and the 7 were certain because they were based on graduations or markings on the device. And this 5 was our estimated digit. And it's actually a 4. And so if we count up the number of certain digits plus estimated digits, the total number of certain plus estimated digits gives us the number of what we call significant figures for this measurement. So in ruler A, we have 1 certain digit plus 1 estimated digit equals 2 sig figs. And in ruler B, our measurement 3.74, we have 2 certain digits plus 1 estimated digit equals 3 sig figs. So the number of significant figures in measurements is really important because it tells you when you write down a number, how much of the number you knew with certainty and in what place in the number you were estimating. So the significant figures in a number or in a measurement are all the digits that are known with certainty plus that 1 estimated or uncertain digit. So how do you record measurements that contain these uncertain or estimated numbers? So when you're recording a measurement using an analog device like a ruler or a graduated cylinder, something where you're reading the device yourself as a human, you always estimate between the lines or graduations on the measuring device to obtain that 1 uncertain digit. And if you're using a digital device, the last digit on the digital display has already been estimated for you by the measuring device. Just because it's digital doesn't mean that there's not an estimated digit. It's just that the digital device is doing the estimating for you. So again, both analog and digital measuring devices are going to produce still 1 uncertain or estimated digit in the measurement. Okay, so how do you take a measurement with the correct number of sig figs on an analog device? And this will be really important in experiment 1 when the whole lab is based on taking measurements and recording the correct number of sig figs. So to take a measurement on an analog device, you want to determine what each graduation or line on the device represents because the markings show you the certain digits. So let's say we're reading this graduated cylinder that's pictured. We'll say that it's in units of milliliters. And so we can see that we have markings of 1 to 2 milliliters. And then in between, we have smaller graduations. And if we count them, there's 10 graduations between the 1 and the 2. So that means each graduation represents a tenth of a milliliter. So this would be 1.5. And that means this here is 2.5. So when we take a measurement, we're going to know with certainty that our measurement goes out to the tenths place, because each marking represents a tenth of a milliliter. So when we take our measurement, we need to estimate between these markings to get our one uncertain digit. So if we look at our liquid level here, when you're measuring liquids in a graduated cylinder, you measure the liquid at the bottom of what's called the meniscus. The meniscus is this curve in the liquid, and you always want to take your measurement at the bottom of the curve. So if this is our measurement point, we know with certainty that it's between, say, 2.6 and 2.7. And so we need to estimate how much between 2.6 and 2.7 it actually is. And to me, it looks like it's exactly between 2.6 and 2.7. So I might record this measurement as 2.65. So my uncertain digit is that 5. That's the one that I had to estimate. So if we count up how many sig figs we have in this measurement, we have all the certain digits, the 2 and the 6, plus that one uncertain digit equals 3 sig figs total. And it's important to write down all of these, even if the last digit is a 0. And this is where students, I most often see them potentially get marked down on the first lab, is if your last reading is a 0, it still needs to be written down, because if you drop off the last 0, it makes it look like your estimated digit was in the tenths place instead of being in the hundredths place. So when we talk about measuring devices, scientists are often interested in the precision of the instrument. When we talk about the precision of the instrument, we're just talking about in what point do you make the estimated, do you make your estimate for the measured value? So in our example, I estimated that the liquid level was at 2.65 milliliters. So the estimated digit was in the hundredths place. Which means our uncertainty or precision of the instrument is 0.01. And what this means is that we would expect anyone else taking the same measurement to be within 100th of what I also estimated. That there's an expected amount of uncertainty when someone takes a measurement with this instrument, because you have to estimate between the lines. But it's reasonable to assume that everybody's estimate would be about plus or minus 1 from whatever the uncertain digit is. When you're using a digital device, the digital device is doing the estimating for you. So the precision of the device is the location of the last digit. So if we look at this digital thermometer pictured here, it reached 36.4 degrees Celsius. So the 4 is the last digit to the right. It's the smallest inclination or smallest division on the measuring device. So that means our precision on this measuring device is plus or minus 0.1 degrees Celsius, a tenth of a degree Celsius. So that means we would expect our true reading, or the accepted range for the reading, really to be 36.3 degrees Celsius to 36.5 degrees Celsius. That's kind of the expected range, because if we took our measurement at 36.4, but we know this last digit is estimated, and it's expected that a reasonable amount of error would be plus or minus 1 from our estimated value, the range of the temperature is actually 36.3 to 36.5. With a digital device, it's doing the estimating for you, so you just write down every single digit that's displayed on the digital device. And then whatever the last digit is, that's your estimated value. So again, volumes in a graduated cylinder, they're going to be determined by reading the volume at the bottom of the meniscus. So let's take a look at this graduated cylinder pictured. What volume range on the cylinder do we know with certainty? what digits should we estimate? Is it going to be in the tenths place, the hundreds place, the thousandths place? And then how many sig figs will our volume measurement actually contain? So if I take a look at this, again, I forgot to put the units on here, it's in milliliters. We can see that we go from 1 to 2 milliliters, but there's markings in between. So let's count how many there are. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So each marking represents a tenth of a milliliter. So this would be 2.1, 2.2, etc., up to 2.5, 2.6, 2.7, 2.8, 2.9, and 3. So we know with certainty that the bottom of our meniscus is between 2.6 to 2.7. Because that's based on the markings that we can see. So to get our measurement, we need to estimate between the lines or the markings to get one uncertain digit. So you kind of divide the space into tenths, and then you estimate as close as you can where the line or where the liquid lies between those two lines. So I think it's pretty much right in between. I might say it's a little bit closer to 2.6 than 2.7. So I might say it's 2.64. Another person might say it's 2.65. It's a 6. Maybe somebody would say it's 2.66, but kind of right in this range. And so the estimated digit is in the hundreds place, which tells us the precision of the measuring device is plus or minus 0.01. That you would expect if you took a good measurement for any other measurements taken to be plus or minus that same estimated digit, plus or minus 1. So if we count up the sig figs, our certain digits are the 2 and the 6, and then plus our 1 estimated digit, we have 3 sig figs in this measurement. So again, when you're recording measurements, you always include the certain digits plus 1 estimated digit. If you are taking the measurement from an analog device, it's up to you to come up with the estimated digit. If it's a digital device, it does it for you. And so it's important that you write down all of the digits displayed on the screen so that you don't accidentally, with a digital device, leave one off. Okay, let's do another practice. So what are the graduations or the distance between the marks on this ruler? What could we say the precision of the ruler is? What numbers would you record when measuring the black piece of fabric? How many sig figs would your measurement have? And what digits in your measurement are certain and what digits are uncertain? So let's first figure out what measuring device we're looking at, what the graduations are. Let's work in the metric system, so we'll call this centimeters. And if we count the number of lines, we have 40 to 41 to 42. So we have large markings every 1 centimeter, but let's count how many small hashes or marks are between. So there's 10 marks in between, which is great. A lot of the metric system, like I said, it's based on units of 10. So with most metric system measuring devices, you're going to have main markings every 1 unit, in this case every 1 centimeter, and then you'll have hash marks quite often every 10th of that unit. Okay, so we know that the distance between the marks is 0.1 centimeter. So what is the precision of this ruler? The precision will be plus or minus 0.01 centimeters, because if the markings are every 10th of a centimeter, and then when you take a reading, you estimate between the marks, you're going to be estimating one more place over to get that estimated digit. So the precision is where that estimated digit is going to be, which is going to be in the hundredths place. We know with certainty what the length of the black fabric is out to the tenths place, and then we're going to estimate between the lines, between the tenths markings, to get a number in the hundredths place. So let's try to figure out how to measure this. Say it's right there. So I'd say that's between 41.6 to 41.7. And now we have to estimate how far between the 0.6 and the 0.7 it is. And I think it's closer to the 0.6. I'm going to erase my line so I can see a little better. I'd say 41.64. And you reading this, you might come up with a slightly different number. You might say it's 41.65, 41.63, but let's write down what I came up with. So 41.63. So how many significant figures does this measurement have? It's all the certain digits plus the uncertain ones. So we recorded all the certain digits. We knew with certainty it was between 41.6 and 41.7, plus the uncertain digit gives us 4 sig figs total. And then what digits in the measurement are certain and what digits are uncertain? The 4, the 1, and the 6 are certain. And then our 3 is uncertain. And the 3 is uncertain because it was that last estimated digit. Okay, let's try another one. So based on this digital scale, what is the measurement? And this is measuring in grams. So jot down what you would record in your lab manual if you were looking at this in a lab. What digits are certain and what digit is the uncertain digit? And then how many sig figs would you have when you recorded this measurement? So our measurement, you write down all the digits on the scale. So 1.102 grams. Even if this last number was a 0, you'd still write it down, 1.100 grams. You don't want to accidentally drop off these zeros if your last digit is a 0. In this case, it's not, but I always like to point that out. Okay, so our measurement is 1.102. What digits are certain? So all the digits up to the last one are going to be certain. So the 1, and the 0. And our uncertain digit is the 2. And so our number of sig figs is the number of certain digits, 3 certain digits, plus our 1 uncertain. So we have 4 sig figs in this measurement. So there are some guidelines for determining the number of sig figs. When taking a measurement, which is what we've been talking about, you determine the certain digits and the estimated digits based on the lines or graduations on an analog measuring device, or you write down all of the numbers on a digital device. And then all of the certain digits plus the 1 estimated digit count as the significant figures. When you're using measurements and calculations, we're going to use set guidelines to determine the number of significant figures to include in an answer after we've performed mathematical operations on a number that has sig figs. So what's going to be happening is you take a measurement in the lab or you're working with a number in a calculation that comes from a measurement, and you perform a mathematical operation on it, like you multiply it or you divide it or you add it or you subtract it. And because your number had sig figs, it had some uncertainty with it, we have to keep track of the number of sig figs throughout the course of the mathematical operations to know how many digits, how many numbers we can include with our final answer, so that the final answer after performing mathematical calculations reflects the amount of certainty that we had at the beginning of our calculation. And so when we start talking about mathematical operations in sig figs, which is next, that's what we'll be talking about how to do. All right, that's it for this section. I'll see you next time.